Okay, welcome to the second video on vectors and scalars. All right. In the last video, we talked about vectors in 2 dimensions. We talked about how we add vectors using graphical methods such as the head-to-tail method and the parallelogram method. Okay. We also talked about vectors in 1 dimension, multiplying them by scalars, and how that can possibly change the direction if the scalar is negative. Now we're going to talk about basic right-angle trigonometry. And the reason why this is important for us to go over trigonometry is because we use component vectors a lot. And this idea of component vectors is very important. Again, you will be using this over the course of the next 2 years in physics, all right? So component vectors are vectors that point in the same direction as the x and y axes in the Cartesian coordinate system. Component vectors are often shorter than the actual vector that you're representing by components, but they can never be longer. They can only ever be the same length under certain circumstances, and that will become clear a little bit later. Okay. All right, so we call component vectors, we give them a subscript x or y. So, for example, if I have this red vector r, okay, I would represent the component vectors as r sub y and r sub x, okay? And you can see that r sub y and r sub x in this case are lined up head to tail, and when I add them together, they give the vector sum of r. And what is useful about this is the angle between rx and ry is a right angle. So I can use right angle trigonometry to help me solve this problem. It's a very powerful method, okay? Again, components are always at right angles to one another. This vector can be thought of as the hypotenuse of a right triangle, then, the actual vector that you're breaking into components, okay? With one of the x and y components as the other 2 sides of the triangle. Here's another example. Here r is going up to the right, okay? This angle is theta. This angle is always 90 degrees, or pi over 2. In this case, r sub x is the longer one, pointed to the right, and r sub y is positive, pointed up. So again, I just want to remind you that in the Cartesian coordinate system, up is positive, down is negative, to the right is positive, and to the left is negative. So that's going to hold here when we talk about component vectors. It's good that we're all on the same page with that. Okay, homework study packet number 1. All right, go ahead and pause the video and try to draw the x and y and label the x and y components for each vector a, b, c, and d. Okay, so a is pointed down to the right, so ay is negative, but ax is positive, something like that. Okay, vector b is up to the right, so both bx and by are positive. Okay, c is a long vector pointed way up top at just a slight angle to the left, so cy will be much longer than cx, and cx is negative and cy is positive. And vector d, which you may feel like is slightly tricking you, that is dx, okay? It's all x component. There is no y component to d because it's pointed directly in the positive, along the positive x-axis, okay? Homework study packet number 2. You can pause the video and try to do these. Okay, now I'm giving you component vectors, and I want you to draw and label the resultant vector, okay? Now, the first one's quite easy. I've got them lined up head to tail, ex and ey. Ey is negative, ex is positive. So the resultant vector E is like that. In the case of fx and fy, they're lined up head to head. So I guess what you'd want to do is you'd use the parallelogram method here. You could also move fx and fy such that you line them up head to tail and use the head to tail method. It's up to you. Okay? Okay. In this case, now this is not right, okay? This is called g sub x. This is obviously g sub y. This is a mistake. Go ahead and make this correction. G sub x is obviously 0, and g sub y is non-zero. Okay, so g sub y is equal to g in this case, all right? H sub x here is negative. H sub y is positive, okay? But when you add them together, you get h, which points up and to the left, okay? Okay. So let's go back to this diagram. You know about basic right-angle trigonometry. You know the Pythagorean theorem tells you that rx squared plus ry squared equals r squared. And so if we want to find r, we take the square root of all of this stuff on the right-hand side. Okay? Trigonometry tells us the following. The sine of theta is the opposite side over the hypotenuse, which is r sub y over r. The cosine of theta is the adjacent over the hypotenuse, which is Rx over R, and the tangent is the ratio of the opposite and the adjacent sides, which is, in this case, Ry over Rx. I'm assuming that you're good with that you know how to do that, okay? Now, R is the resultant vector of Rx and Ry, both by the head-to-tail method and the parallelogram method, okay? Doesn't matter how you think of it, whether head-to-tail or parallelogram, R is the resultant vector. Rx and Ry can be positive or negative, right? Positive Ry is upward, negative Ry points downwards, and as I've said before, positive Rx points to the right, negative Rx points to the left, okay? Still the same triangle here, okay? What's really, really useful is to be able to use inverse trigonometric functions, okay? So if I'm given this triangle and we need to find the angles, what we would use is the inverse trigonometric function, okay? So for example, theta, we can express it one of three ways, all right? We can say that theta is the inverse of Ry over R. In other words, theta is the angle for which the sine is Ry over R. Does that make sense? It's also the angle for which the cosine is Rx over R, and it's also the angle for which the tangent is Ry over Rx, okay? On your calculator, you might see these arc sine, arc cosine, arc tangent. Just go ahead and use degrees for all angles for now. And one thing I'll talk about in class, I'll show you why this is. Note that sine to the -1 is the inverse sine or the arc sine. It is not 1 over sine. Okay, that is a huge dangerous thing to assume, and we'll talk about that a little more in class. If you can't wait for class to talk about that, then you can play around with your calculator and you can put in some values and you can see clearly it's not going to be the same thing. Okay, all right, homework study packet number 4. Go ahead and pause the video and try it. Okay, so I give you a vector, I give you the components, okay, and I'm asking you to determine the resultant vector graphically and analytically. So you're going to need some graph paper for this, all right? So I've drawn it here on graph paper, okay, and I've chosen a scale where 1/2 centimeter is 1 meter. It's up to you to decide your scale. Either way, you're going to get a similar triangle to this one, okay? So here's my positive 17. Here's my positive 8. So the resultant vector goes up and to the right. Okay, so so graphically, when I say graphically, it means just draw it, and then you can just use a ruler to estimate what the length is. I got about 18.2 meters using the scale, and I used a protractor, and I got about 25 degrees. Now I was really careful about drawing them. Now, analytically, let's do it. So you can use, since you're given the opposite side and the adjacent side, and you need to find the hypotenuse, just use the Pythagorean theorem. S is the square root of sx squared plus sy squared. I got 19 meters, and then just use the inverse tangent to find theta, and I got 25 degrees. So you see, my estimates when I'm doing it graphically were actually quite good in terms of matching what I got analytically. Okay, so pause this video if I'm going too fast. Make sure you understand this problem because they're going to get more and more complicated as the slides go on. Okay. Now, another thing that you can do, we're going to play around with this in class, is this is a PhET simulation, the vectors simulation, and there's a link to it on the web page. It's a lot of fun to play around with. So we could actually do this problem with the PhET simulation. It's not cheating because it's fun, and we've already done it using the traditional method. When you do it, I've taken a screenshot of the result. Here is 25.2 and 18.8, which with sig figs rounds to 19, so we're good there. Okay? Okay. Homework study packet number 7. It's getting a little more complicated. Go ahead and try this one. You're going to need graph paper for this. Okay, so I've drawn it, and I have something like this. Okay, I use a scale of 1 centimeter equals 10 kilometers. I'm calling, let's see, an eagle leaves his nest and flies 22 kilometers north. I'm calling that segment number 1, which is this vector right here. He then flies in a direction 60 degrees south of east for 47 kilometers. I'm calling that segment 2, which is right here. What's the eagle's displacement from his nest? Okay, his displacement. In other words, what is the resultant vector, which is a vector drawn from where he starts off right here to where he ends up, which is down here, and I've labeled that by S, okay? So that's your, a lot of times you're going to have to read the problem a couple of times and really draw your diagram to really understand what it is you even asked to find. And the other advantage of drawing a diagram is that you can see whether or not your vector, the values are even in the ballpark of reality. Okay, so I can see that, you know, the length of this vector is going to be somewhere between the length of S1 and S2. So in other words, the length of S is going to be between 22 kilometers long and 47 kilometers long. And this angle looks to me like it's, I don't know, maybe around 45 degrees or something. I don't know. I don't even know what that would be, okay? But it looks like it should be between 0 and 90, maybe a little less than 45 degrees, okay? So let's see. So a couple of things that we notice here, okay? My subscripts can get a little bit confusing, okay? So because we have three vectors, S1, S2, and S, we can have such things as S2y and S2x, okay? Because those are component vectors of S2, for example, okay? So S2x is right here, and S2y is right here. I just drew the arrowheads, okay? And I note that the sine of 60 and the cosine of 60 are as follows, okay? Now, I'm doing something here that I haven't really taught you yet, and that is making a table of my x and y components. So if you're not following completely right now, don't worry, I'll explain it to you in the next video. But I'm basically just drawing the x and y, computing the x and y components of S1 and S2. Okay, I add them together to get the x components of x, okay? And then I use those x components with the Pythagorean theorem to find a length of s, which is 30 kilometers. Remember what I said before? I said visually it looks like s should be between 22 and 47. Well, obviously it is, okay? And I'm good with my sig figs, I think. And then I use the inverse tangent function to get 38.5, okay? And that inverse tangent function is referring to the following right triangle, which I'm drawing right now in red. It's that right triangle right there, okay? Where this is the opposite and this is the adjacent, okay? So I have sy over sx. So you really want to study this diagram again to make sure you understand it before you move on, okay? I can also do this with the PhET program. So this is what it looks like. We'll do this together in class, but you can see that I get the same results, about the same results when I use the PhET program. So pretty cool. Okay? All right. This is a very important problem that we're going to spend quite a bit of time on. This is the inclined plane. You will see this again when we study forces. Go ahead and read the problem and give it a try. Okay, so I have vector W acting downwards. It could be the weight vector on a box or something located at resting on this inclined plane. Okay, all right. Now, if the weight vector is 12.5 newtons acting straight downwards, and this angle is 23 degrees, I want you to draw and compute the components of the vector. Now, this is pretty cool. All right. Notice how I have tilted my Cartesian coordinate system such that the x-axis is now at an angle 23 degrees above x equals 0. Okay. So again, this is my x-axis. This is my y-axis right here. All right. And then I draw the y and the x components as such, and you can see, and I can prove this to you in class, that this angle right here is also theta. So this triangle right here, this original right triangle, and this right triangle are similar triangles. You should prove that to yourself. It's very, very important. Now, for the small triangle here, it becomes really, really easy to figure out what wx and wy are if you believe that theta is 23 degrees in there, okay? So go ahead and check my work, all right? I'm saying that wx equals w sine theta and wy equals w cosine theta. I solve them like this. Proper sig figs, are we good? 3, yes, we're good to go. Okay? Now, notice that w sub x is parallel to the inclined plane and wy is perpendicular to the inclined plane. And that's because I cleverly rotated my entire Cartesian coordinate system such that the plane was the x-axis, okay? So we're going to do that all the time when we deal with forces and things on inclined planes. This is a very important problem for you to understand, okay? So in summary, when I add vectors, let's say I have 3 vectors, a, b, c, in 2 dimensions, okay? Obviously, I can say that a is the sum of ax and ay, b is the sum of bx and by, and c is the sum of cx and cy, obviously, okay? Turns out that if I add them all together, r equals a plus b plus c, because r itself has 2 component vectors, rx and ry, okay, it must mean that Rx equals Ax plus Bx plus Cx, and Ry equals Ay plus By plus Cy. Okay? We will use this all the time to solve vector problems. This is crucial to us using that table with the rows and columns where we had two columns for the x component and the y component and adding them up. You'll see what I mean in the next video. Super important. Therefore, again, the x component of R is the sum of all x components of A, B, and C, and the y component is the sum of all y components of A, B, and C. So we're getting a little more complicated. We'll check out the next video to get even more in depth into this topic.